Hello, let us continue our discussion on the geometry of closed packed structure. In this video, we will look at the voids in the closed packed structure. We have already looked at the lattice and motif structure of various crystal structures which form by closed packing, in particular two of them ABAB and ABC, where ABAB form hexagonal closed packed and ABC form cubic closed packed. Now, in these closed packed layers between the atoms there are spaces available. These spaces can accommodate other elements or other atoms. So, in the structure of alloys or solid solutions, which we will come to soon, these voids are very important. So, let us look at the geometry of these voids. First, let us look at what kind of voids and where they are located. So, one of the important kind of voids which is there is the tetrahedral void. Now, tetrahedral, the adjective tetrahedral comes from tetrahedron, and a regular tetrahedron is a solid bounded by 4 equilateral triangular faces. A pyramid based on equilateral can also be called a pyramid based on equilateral triangle. Tetra means 4 and hedron faces. So, 4 faces, these 4 faces are equilateral triangles in a regular tetrahedron. So, where do we form such equilateral triangle in our closed packed structure? So, this is a layer, familiar layer, one layer of closed packed spheres which we are calling A layer. In this A layer, the location of B and C sites are also marked. So, the next layer, if we consider the next layer to be the B layer, so the B atoms set on these sites above A atoms. So, let us look at one of those atoms. So, on this triangle of 3 A atoms, we locate a B atom at its centroid. So, this B atom is sitting on these 3 A atoms. So, it is touching each of these 3 A atoms. This forms a regular tetrahedron. The centroids of these 4 spheres form a regular tetrahedron. Similarly, if we look 3 B centers here located above an A sphere. So, if we place these 3 B atoms and concentrate on these 3 B atoms, then we find that the A atoms comes from below and closes the void between these 3 B atoms. So, again the 4 atoms, these 3 B with a single A atoms from below also forms a tetrahedron. The centroids or the centers of these spheres form a regular tetrahedron. The space left between these spheres is the void which is given the name tetrahedral void. So, we can see that between two layers, between two closed packed layers A and B, we have tetrahedral voids, and there are two kinds of tetrahedral void. One is the upright tetrahedron with a base of 3 A atoms and B atom coming on top, or with a base of 3 B atoms, an A atom coming from below will give us an inverted tetrahedron. So, tetrahedral voids are there between two layers of closed packed spheres, and they are in two different orientations, upright tetrahedron and inverted tetrahedron. Let us now look at the other kind of void. The other important kind of void is the octahedral voids. This also forms between two closed packed layers. Again we start with one closed packed layer, the A layer, and we focus on the C site. Around this C site there are 3 A atoms in its own plane, and above this C site in the next layer there are 3 B atoms, and of course, between these two the C site is unoccupied. Between two closed packed layers A and B, there is an unoccupied C site. So, between any two layers, if we see the location of these unoccupied sites, the C site, we get an octahedral void. Again, octahedral void comes from the name regular octahedron, which is a solid bounded by 8 equilateral triangles. Octa is 8. So, 8 equilateral triangles define a regular octahedron. This solid can be also considered as a bipyramid based on sorry, it is a bipyramid based on equilateral triangle. Let me fix this. It is a bipyramid based on a square, not equilateral triangle. So, it is a bipyramid based on a square, on a square. So, a bipyramid based on a square or a triangular antiprism. So, this is a definition of regular octahedron, and the location of that regular octahedron can be seen here, as I was telling, around a C site. So, when we place the B atoms, there are 3 B atoms around this C site and there are also 3 A atoms below. So, 3 A atoms on one plane and 3 B atoms on another plane, the centers of these 6 spheres are 6 corners of the octahedron. So, octahedron has 8 faces, but has only 6 corners. So, you require 6 spheres to define the octahedron, and the space between them is the octahedral void. So, that is the triangle of the B atoms on top and another triangle of A atoms, an inverted triangle of A atoms below. That is why there are 2 triangles in a solid bounded by a bottom triangle and a top triangle, and 6 triangular faces, other 6 triangular faces, making total 8 triangular faces. So, a top triangle, a bottom triangle, and other 6 triangles are inclined triangles. So, that is why it is called, since the top and bottom triangles are not parallel. If they were parallel, we would have got a prism and the side faces would have been rectangles. But since the top and bottom faces are inverted triangles, we get an antiprism with 8 equilateral triangles. So, this is the space between such a solid is an octahedral void, and with this we now finish with the slides and let us come to the pen and paper, where we will like to derive the size of these voids. So, let us look at the size of tetrahedral void. By size we mean the radius of the largest sphere that can fit inside the void without displacing atoms or spheres. Since I am using a sphere, let us continue with that terminology, without displacing the spheres at the corners defining the void. This is how we define the size of a void. So, let us look at a tetrahedral void. We have seen that a tetrahedral void is defined by 4 spheres, 3 spheres on a base making an equilateral triangle, 3 spheres on a base making an equilateral triangle, and 1 sphere on the top. One sphere on the top making this a tetrahedron. So, in perspective, if I try to draw this tetrahedron, so I have a base of an equilateral triangle. So, now I am representing that by let us say A, B and C, and I have a sphere on the top sitting on this A, B and C. So, now I am showing only the centers of the sphere. So, the center of the base spheres are A, B and C, and center of the sphere sitting on the top is D. So, if I join these, this is where I get my tetrahedron. You can imagine a tetrahedron of the shape. Now, if we want to find the radius of this largest sphere, that is what is the size which will fit in this tetrahedral void. Let us try to work that out by first looking at the base triangle ABC. So, let me try to draw the base triangle ABC. And let me drop a perpendicular from A to the other side, AP. The centroid of the triangle will be on AP at some point Q, which divides the height AP in a ratio 2:1. This we know from geometry. So, let us locate this centroid in terms of our radius of atom. So, the diameter, let us say that the diameter of the spheres making the close packed structure is 2r. So, r is the radius of spheres forming the close packed structure. So, the edge length of the tetrahedron of the tetrahedron, that is AB, BC, CA or AD, any of these edge length of the tetrahedron is equal to 2r, because atoms are in contact along these edges. Atoms touch along the edges. So, AC, for example, AC becomes 2r and PC, which is half of the edge, becomes R. So, this quickly gives us the height AP of the triangle. This is just the geometry of equilateral triangle. So, AP in this triangle APC, in the triangle APC we have APC as 90 degree, that is the right angle. So, AC is the hypotenuse. So, AP square AP will be, by using Pythagoras theorem, AC square minus PC square, which of course becomes AC is 2R. So, 4R is square and PC is R. So, R is square root of this. So, which means AP is nothing but root 3 R. AP is root 3 R. So, let us continue with this on the next page. So, let us draw our triangle again. This is Q, the centroid of the triangle. ABC is the equilateral triangle. AP is perpendicular from A on BC, and we have PC is equal to R, and we have AC is equal to 2R, and we just found that AP is root 3R. Now, since AP is divided by the centroid Q, AP is divided in a ratio 2:1. So, we have AQ 2/3 of AP, which means 2/3 of root 3R, which gives us 2 by root 3 R. AQ is 2 by root 3 R. So, let us continue with this now. Let us look at the full tetrahedron. So, our full tetrahedron was something like this. This was our A, B, C, the apex D. From D, if we drop a perpendicular, this meets the centroid Q. This again from the geometry of the tetrahedron, and from if we now join AQ. So, the next triangle which we will focus on is this triangle. From the top corner D, we have dropped a perpendicular on the base ABC, which also is exactly at the centroid of the base ABC. So, that is a DQ, and we have A. We have already found AQ, which is 2 by root 3 R. AD is again edge of the same tetrahedron, and this is a regular tetrahedron. All edges are equal. Along AD also atoms touch, because this D is the top atom, the B plane atom, which is touching with the A plane atom. So, AD also is 2R. So, we can easily solve now the height of the tetrahedron. height of the tetrahedron dq is equal to dA square minus AQ square square root of this quantity. dA square is 4r square minus AQ, which is 2 by root 3r. So, it is 4r square by 3. So, this will be square root of 8r square by 3, which gives us 2 root 2 by root 3 r. So, we have found the height of the tetrahedron in terms of the radius of the atom. Now, the centroid of the overall tetrahedron, is located on this height in such a fashion that it divides the height into 3:1. So, let us call this centroid T. T is the centroid of the tetrahedron. So, dt will be 3/4 of the height of the tetrahedron dq. So, 3/4 of 2 root 2 by root 3 r, which is nothing but, we cancel here 2. So, we can see that we can write this as root 3 by root 2 r. So, dt is root 3 by root 2 r. Now, let us look at D there is a sphere of radius r sitting. At D, a sphere of radius r is already sitting. At T is where the void atom can sit, and the largest void atom will be one which just touches this outer sphere. So, this is the largest sphere R T. So, largest sphere that can fit in the void will have a radius R T such that R T plus R is equal to d T root 3 by root 2 R. This is because along this line, along the line d T, the two spheres should touch. So, the sum of their radii, the sphere which is fitting in the tetrahedral void R T and the sphere which is sitting at the corners of the void, which is defining the void capital R. So, the sum of these two radii should be equal to the distance between corner and center, which is what we have found d T, which is root 3 by root 2 R. So, now it is a simple matter to calculate the distance R T. So, R T becomes root 3 by root 2 minus 1 R. So, we have solved the radius of the tetrahedral void or radius of the largest atom which will fit in the tetrahedral void as root 3 by root 2 minus 1 r. If we solve this numerically, we find that this is nothing but this is approximately equal to 0.225 r. So, the radius which can fit, the sphere which can fit into a tetrahedral void without disturbing the surrounding spheres will at the most will have 22.5% of the radius of outer spheres defining the void. So, this is what we call or this is what we mean by the phrase size of the tetrahedral void. Let us continue with our discussion to find the size of the octahedral void. This is actually much simpler because the geometry of octahedral void is much simpler. So, now let us look at size of the octahedral void. Now, octahedron, as we saw when we made the octahedral void, we had 3 atoms below like this, and we also had 3 atoms above like this. This is how an octahedron will sit on a table, it will sit on its triangular face. However, for calculation purpose, it is more easy to do the calculation if we stand the octahedron on one of its diagonal. If we make one of the diagonals vertical, then we find that it can be considered as a square of 4 atoms or 4 spheres with one sphere sitting on the top and one sphere sitting on the bottom. So, essentially this becomes a square based dipyramid. This is the two phrases which I had used in the slide. Either you can consider it as triangular antiprism, or you can consider it as a square based dipyramid, because there is a pyramid on top and there is a pyramid at the bottom. Since it is a square, looking at it from the square based dipyramid approach makes the calculation much simpler, because geometry of a square is much simpler than geometry of triangles. So, we have, let us say we have this squares, and on the corners of these square these 4 atoms are sitting, which are exactly touching along the edges. I am trying to draw. These are the 4 spheres which are sitting on the corner of that square. I have shown them actually touching here, I had not shown them and touching for clarity, but actually they are touching. So, you can see that the side length of this square now, just like the edge length of the tetrahedron was 2 r, the edge length of octahedron also is 2 r. So, the side of the square also is 2 r. The largest sphere that can fit into this void now will be sitting somewhere here, and this will have a radius r o for octahedron. So, if we see now, if we connect this diagonal, we can see that the full length of the diagonal of this square is root 2 times the edge length to root 2 r. However, we can see that along that diagonal my red sphere contributes a radius r from this corner and a radius r from this corner, whereas the central sphere, the one in the void, is contributing 2 r o. So, if I write that expression now, that the diagonal of the square can also be written as 2 r plus 2 r octahedral, and this will give me 2 root 2 r. Once we realize this, it is easy to come up with a final result. Of course, we can cancel 2. So, r naught is nothing but root 2 minus 1 r. Or if you do it numerically, you can show that r naught is equal to approximately equal to 0.414 r. So, we can see that in close packed structure, we can use the next page. Let us summarize. In close packed structure, two kinds of voids are present. One is the tetrahedral void, which comes in two orientations, upright and inverted. And octahedral voids, which come only in one orientation. And we computed the sizes of these voids also. by showing that the radius of the atom, largest atom which can fit in a tetrahedral void R t was approximately 0.225 r, and the radius of the octahedral void was 0.414 r. So, obviously, the octahedral void size is larger than the tetrahedral void size. Let us continue the discussion on the voids by seeing where these voids are located in the unit cell of CCP and HCP. So, location of voids inside in a CCP unit cell. So, let us draw a schematic CCP unit cell. Now, let me not draw the atoms in full size, because that of course will make it too complicated. So, I draw smaller atoms. The corner atom, as well as, since it is CCP, the face center atoms. Now, if we look at, let us locate the tetrahedral void. So, let us look at one corner, and at every corner three faces meet. So, in this corner the top face, the right face and the front faces are meeting. So, let us look at those face centers which are meeting at our selected corner. So, the top face center, the front face center and the right face center. These four atoms, let me claim that these four atoms form a tetrahedron. Each of these edge lengths, you can easily compute each of these edge lengths in terms of the lattice parameter A. This is, each of them is equal to half face diagonal. So, they are A by root 2. Each faces are equilateral triangle, and that is where you have a tetrahedral void. This tetrahedral void is totally inside the unit cell. You can see that the bounding edges are all either on the face of the cube or inside. So, one tetrahedral void from each corner. center of this void will be located on the body diagonal. Center of this void will be located on the body diagonal. Body diagonal. So, since one tetrahedral void from each corner is there, in the entire unit cell from this, in the unit cell of CCP, there are 8 voids. But if you look at the number of atoms in the unit cell, so there are 8 corner atoms, but effectively only 1/8 of the corner atom belongs to the cell, because each corner atom is shared by 8 unit cells. So, corner atoms shared by 8 unit cells. And there are 6 face centered atoms, and they are shared by 2 unit cells. So, effectively half of that belongs to each unit cell. So, we get 4 atoms per cell. So, this gives us a calculation of number of voids per atom, number of tetrahedral voids per atom, number of tetrahedral void per cell by number of number of atoms per cell. This is 8, this is 4. So, you get a nice number 2. So, there are 2 tetrahedral voids per atom, 2 tetrahedral voids per atom. Similarly, we can try to locate the octahedral void in the cell. Let us start with our cube. Top and face center, left and right face center, and the front back face center. So, if you look at this, the octahedral void is located right in the center of the cube, because these 6 face center atom, if you look at these 6 face center atoms, they are 6 corners of an octahedron. These 6 atoms define nicely 6 corners. So, if we join the 4 centers of the 4 horizontal faces, you get a nice square, and then the top and bottom then give you the 2 pyramids. Complete our octahedral void. So, OH void located at the center of the cubic unit cell. Not we are trying to work out octahedral void in CCP. So, OH void is located at the center of the cubic unit cell, but interestingly, if you now look at the geometry of this centroid, the center of the octahedral void is center of 6 atoms, and the location of those 6 atoms are one forward, one backward, one on the left, one on the right, and one top and one bottom, and each of them are at a distance a by 2. So, a by 2 right, a by 2 left, a by 2 up, a by 2 down, a by 2 front, a by 2 back. With this in view, if you now examine the center of the edges of the cube, you find that the center of the edge is also an location of an octahedral void. Also at the edge centers, because you can see if I go from here, a by 2 front I have an atom, a by 2 back I have an atom, a by 2 left I have an atom, a by 2 right I will have an atom when I consider the next unit cell. The unit cell on the right will provide an atom exactly at a by 2 to the right of this center. Similarly, I have a by 2 bottom, but a by 2 top come from the next unit cell. So, if you imagine that way, it is easy to see that octahedral void is also at the edge centers of the unit cell. So, the numbers here can now be calculated. So, number of octahedral voids per cell. The central void is totally included in the cell. So, I have 1 from center of cube, plus I have 12 voids, there are 12 edges of the cube. So, I have 12 voids located at the edges, but since one edge, if you look carefully in the 3D structure, one edge, each edge is shared by 4 cubes. So, effectively only 1/4 of the void belongs to each cube. So, 12 from 12 edges and 1/4 because each edge shared by 4 cubes. So, this number then comes out to be 4. So, the number of voids per atom here becomes simple, number of octahedral voids per atom is equal to number of octahedral voids per cell divided by number of atoms per cell. Both of them are 4. So, we get a nice number 1. So, there is one octahedral void per atom in a cubic cell, 1 OHV per atom. So, with this all this geometrical study or geometrical study of the voids in the structure, we now complete this topic and we will next look at the role of the voids in forming different kinds of solid solution. So, that we will do in a future video.